Hello, 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 hello. Uh, am I audible now? I kindly I kindly request all of the participants to use their own name, the registered one, as it is used for the automated attendance. I repeat, all the registered participants, please use your registered name as it is used for the attendance. Good afternoon to everyone. A warm welcome to the second day. Uh, a warm welcome to the second day afternoon session of the workshop. Today we are going to do the practical demonstration and result interpretation of the uh, spectroscopic and uh, microscopic analysis of instruments. So let me introduce myself. I am Rishmi PK, PhD scholar from NITRKL under the Department of Food Process Engineering. So, as a part of this 5-day online certificate course on food analysis and quality control FAQC 2025, I'm doing the practical demonstration and result interpretation of some analytical techniques. Today, we are going to explain high pressure liquid chromatography, UV spectrophotometer, Fourier transform infrared spectroscopy. So, we all know that we need some instruments for analyzing the food sample that we use for food research or in industries and all. So here, each of these instruments is important and play a vital role in ensuring the food safety, nutrition quality, and authenticity. Today, in the presentation, I have included three instruments: high pressure liquid chromatography, UV spectrophotometer, and Fourier transform infrared spectroscopy. Here, I have included the application, limitation, sample preparation, working procedure, result interpretation of all these instruments. So let me start with the high pressure liquid chromatography. So this is high pressure liquid chromatography. High pressure liquid chromatography, HPLC, is otherwise known as high performance liquid chromatography. Its image is shown in the slide. I think you already know about this in the first half session about HPLC. I think you have a thorough idea about this theory part. So we will go for the practical demonstration of the HPLC. So HPLC, you saw the two names HPLC, high pressure liquid chromatography and high performance liquid chromatography. We will explain why the HPLC have the name high pressure liquid chromatography. First of all, we can discuss about this instrument. It is an analytical technique used to separate, identify, and quantify each component present in the sample. It means if we are using a sample for analyzing its compounds present in the sample. First, the instrument will separate all the compounds present in the sample. After that, it will identify each compound present in the sample and it will quantify all those components. So here, the instrument offers a high resolution, speed, accuracy, and reproducibility for analyzing complex samples. Here, we are injecting the mixture of the sample and the mobile phase into the HPLC. So, at a high pressure in the instrument that we are demonstrating here, we are using 0 to 4000 psi pressure for injecting the mixture of the sample plus mobile phase. So, it will give the result very fast so that it offers a high speed for analyzing the complex sample. And for each compound present in the sample will have its own specific retention time so that it can give accuracy in the result also. It involves passing a pressurized sample plus mobile phase mixture through a column packed with a separation medium that is stationary phase. Here we are using silica as the stationary phase which is tightly packed in the column. Through the tightly packed column of the stationary phase, we will inject the mixture and the stationary phase will separate each component present in the sample. This instrument is essential for quality control, pharmaceutical research, food safety, and environmental monitoring. So when we are doing some research work or we are analyzing some samples, we have to know what are the instruments we can use for the analysis of the sample. So before that, we have to know each the specification and significance of each instrument. Along with that, we have to know how to analyze or how to use the instrument for the uh, analysis of our sample. So we have to know why this instrument or HPLC is used in analysis of the sample. Here we can see that HPLC, for HPLC we can use both the liquid and solid samples. Here we have to mix the sample with the solvent, that is the mobile phase. And after mixing the sample with the mobile phase, we have to filter the sample, and the filtered sample will be injected through the to the HPLC. So here it offers a high resolution and sensitivity for complex mixture, and it is suitable for both heat sensitive and non-volatile compounds. Here we can use both volatile and non-volatile compounds. In addition, it provides accurate quantification and reproducible result, and it is compatible with both multiple detectors like UV, fluorescence, MS, PDA detectors for versatility. Here we are using PDA detector. UV detector is a detector which contains, which will emit UV lights through the samples, and some the compounds present in the sample will absorb the UV light, and according to the transmitted light from the sample, we can detect the compound present in the sample. In case of fluorescence detectors, here these fluorescence detectors are used to detect fluorescent compounds. Here the sample will pass through the uh, sample, and some of the compounds that have this fluorescence characteristic, it will emit fluorescent light, and based on the fluorescent light emitted from the sample, it will detect the compound present in the sample. In case of MS detector, it is based on the ratio of mass and ion of the charge of the sample. So mass by charge value, based on the mass by charge value, it will detect the sample. In case of PDA detectors, it is almost same as UV detectors, but in case of UV detector, it will use the range of, it will use only UV light, but in case of PDA detector, it is using a wide range of lights. That is the difference between UV detectors and PDA detectors. Now we can see how the HPLC works. In case of HPLC, we have to mix the sample with the solvent. Solvent is the mobile phase. After mixing the solvent and sample, we have to filter it. It is used to remove the particulates and bubbles present in the sample, as it will increase the inaccuracy of the result. So that we have to filter the sample. So after that, we have to inject the sample into the HPLC, and it will go through the uh, stationary phase, and the as it goes through pass through the stationary phase, the they will interact with each compound present in the sample will interact with the stationary phase, and it will get separated, and based on the interaction, it will give peaks. Each compound will give peaks with a uh, specific retention time. So based on the retention time, we can detect each compound present in the sample. And here we can know that each compound have its own specific retention time, so that we can detect each compound based on its retention time, and it's based on its area. We can calculate this quantity. Here, the separated compounds are detected as they elute using UV visible or fluorescence or mass spectroscopy detectors or PDA detectors, producing a chromatogram for analysis. This chromatogram is used for analysis or detecting the compound present in the sample. Now we can see the application of HPLC. HPLC is used in wide range of industries or research areas. Here, in case of pharmaceuticals, it is used for quality control, purity testing, and drug discovery. And in case of food safety, it is used for detection of additives, contaminants, and quality assurance. For environmental analysis, it is used for measuring pollutants in water, soil, and air samples. And in clinical and biological research, it is used for analyzing biomolecules like protein, peptides, and nucleotides. And it is suitable for a wide range of liquid sample, even in case of complex samples, due to its ability to handle diverse chemical properties. And here also, for example, in case water, we have to detect some specific compounds. We can use the water, we can mix it with the required specific solvent, the mobile phase, and we can filter it, and we can inject into the HPLC, and we can detect which type of compound or which compound is present in the water, which contaminant or which pollutant is present in the water. Like that, we can analyze all these samples. So now we can, like, each and every instrument will have its own limitation. Now we can know the limitations of the instrument HPLC. The high initial cost of the equipment and its maintenance cost is the first limitation that is facing while we are implementing a new HPLC in our lab, and it requires skilled and trained personnel for operation and analysis, as it takes many works during the demonstration or the working of the instrument that you can see in the demonstration video. And it uses expensive and high purity solvents. As the solvents are high purity, needs high purity, it is very expensive, and it is not suitable for insoluble compounds. Many compounds will not be soluble in the mobile phase of HPLC, so that for many some compounds that are not insoluble in the mobile phase won't be suitable for HPLC. Here, it generates a large volume of solvent waste. It is an environmental concern, as we will discuss the mixture of the solvent and the sample, so that it will be an environmental concern. So next we are going to the sample preparation. How we are going to do the sample preparation? Here you can see how we produce the sample.
We are preparing naphthalene sample for in acetonitrile mobile phase for HPLC.
This is how we prepared the sample. Now we can see how we do the demonstration of the working of the instrument. Here I'm going to show. Here, this is the HPLC instrument that is we used for the demonstration. Here they are using the PDA detector. I will show the demonstration of the instrument.
Hi everyone, this is HPLC instrument. HPLC means high performance liquid chromatography or high pressure liquid chromatography. So we have, I'll introduce the parts first. This is the temperature control. This is the pump, binary pump that mobile phase goes through. We have two pumps here, pump A and pump B, and it directly goes to the column. We have a reversed phase column for our HPLC here, and we have a photodiode array detector. And this is the reservoir from where we keep the mobile phase, and it directly goes through the one is pump A and one is pump B. So both goes to the pumps, and after that it goes to the column and directly detect through the detector. When we have both two pumps, because we can either put one mobile phase or we can attach two mobile phases. Now right now I have kept acetonitrile in both the pumps. I have kept acetonitriles. Before passing the mobile phase through the column, we must check whether there is any bubbles or any other particles. There will not be any particles, but we should remove all the bubbles. So for that we only pass through the pump first before passing through the column. So just for that I will keep the flow rate of both pump A and pump B as 0.5 milliliter per minute for both. Then we will remove some amount of mobile phase through the pump. I am just starting the pump right now. So you can see there are few bubbles here in the column, and for that we have to remove the bubbles. There are few bubbles here. Through the syringe we actually remove the bubbles here. Through this you can see the bubbles will be coming outside. we have removed all the bubbles from here. Now we have to pass the mobile face through the columns. So I'll just show you the column also. This is the reversed faced column. The mobile face comes through this part and goes from here, it comes through and passes through the column. This is the C18 reversed column and it goes through the detector. And in the reverse column, actually the mobile face will be polar and column will be non-polar. Now since we have started the experiment, we have to set the parameters for all the instruments. So we go to the instrument menu. Here for the detector, if you want 3D data, you can enable it. Right now we don't want 3D data, so I'm removing it. So 2D channel you have to turn on, and normally we do it at 254 nanometer. If there is a specific wavelength for any sample, you can do at that wavelength. So there is a range from 210 to 400. In this limit, you can keep the wavelength for any sample. This is the requirement for PDA detector. Next we go to the pump. Pump we can set it as isocratic or gradient. It depends on your sample. And for now I am showing the isocratic. Since both the pumps is in acetonitrile, we can keep it in the same way, same flow rate. It's 0.5 and 0.5 for A and both B. The total flow, it would be 1 milliliter per minute. So the highest limit for this pump is the pressure highest limit is 4000, 0 to 4000. So it should be under that limit. And if any temperature requirement it is there, you can keep it. You can keep the temperature. Right now I'm keeping it room temperature only. Now we have to save this method. And my sample is naphthalene, so I just keep it as NAF 1. Since it's saved, we go to the control panel again. You have to save this. First, we have to equilibrate the column because earlier samples presence might be there, or earlier mobile phase presence will be there. So we have to equilibrate with our mobile phase. For that, we click the equilibrate menu, and here you will get the saved method set. Now that we have saved, that is NAF1, and we have to set up that one. Now you can see the flow rate, it came to 0.5 as we have kept it. Again we have to click the equilibrate menu and we just have to equilibrate. For around 10 minutes we have to equilibrate so that it comes around a straight line, or it reduced to around 0.001 something. So until then, for 10 minutes we have to equilibrate this. So after equilibrating, we have to inject the sample now. So we are putting the sample name as SNAP1 itself, and here we can do as inject standard and inject sample. So since this is a sample, I am keeping it inject sample. If you want to do a standard for any sample, so we can keep the inject sample menu. And the method set, as we have kept the method, we will keep it NAF1. Since the retention time for naphthalene is around 7 minutes, I am keeping it, the run time we are keeping it at 10 minutes. So injection volume, it is 20 microliter is enough. Filter the sample.
Now we are going to inject the sample. As I told before, to remove all particulates or bubbles present in the sample, we have to filter it through filtrate. So we are using 0.22 micron filter here.
We are using a 0.2 microfilter. Since our HPLC is manual injection HPLC, we need a certain injection needle to inject it, and we filtered because since all the pipes and columns and the syringe, everything is a capillary tube, there shouldn't be any smaller particles in the sample, so filtering is absolutely necessary. So in this injection also, there shouldn't be any bubbles in the in needle. So we should remove all the bubbles from the needle before injection.
Here we are doing this cleaning of removal of the bubbles because it will affect the accuracy of the result and the result might be wrong. That is why we are injecting a bubble free sample.
This is where we inject the needle. This should be kept straight, and single injection should be done straightly. And just because we have kept 20 microliter, we are injecting 2 times, and from this only 20 microliter will be going into the column and rest will be ejected out. Since we have kept all the parameters, the sample name, function, injection volume, runtime, and we have to press this inject button. Now since indicator comes, we have to use this to inject go the sample into the column. Now the sample is running through the column and the graphs will be obtained. Now we have completed the experiment. Now we have to browse the project for obtaining the graph. We can see the first one as the unknown sample. We have to review it. Now we have to integrate. We can see the peak at 3.091. So the 3.091 is the retention time. If we can, for the graph, we can add the compound name also if that is your requirement. I'm just adding naphthalene. This is the retention time 3.091, and we have to show this in the plot, the chromatogram plot. If there is standard graphs, and we can select it all together and we can calibrate and quantitate the peaks. Since we are not doing that, I'm just clicking the compound name and OK. Now we have to save the result. The program said we have to keep it as nav.
Now we saw how the demonstration of the sample is done. So I already discussed during the limitation part that this is very complicated work to demonstrate or do the HPLC uh, running, so that we need a skilled person for the working of the HPLC. That's a big limitation of the HPLC. Now we are going to see the result interpretation of the result that we obtained from the HPLC.
Now we have obtained the graph, and you can see the naphthalene peak here, and its peak name, its retention time, area, percentage area, and all, and height, all will be shown automatically in the graph. And now we just have to save the report. Since this is the naphthalene graph and the retention time we have got is 3.091, and you can see a small peak at 2.702. That is actually the unretained solutes. It means that it is a small peak that elutes shortly after ejecting the sample into the mobile phase. These solutes do not interact with the stationary phase. They just move through the column at the same rate as mobile phase, and it is slightly detector at first, and it is and then the actual sample is, which is more affinity towards the stationary phase, elute through the column, and it is detected through the detector. And as we know, the chromatographic technique is a technique that separates the compounds in a mixture by the difference in partitioning behavior between the mobile phase and stationary phase. This is just for a single sample. If there is a mixture of samples, for example, fluorine, phenanthrene, and anthracene, this is a sample that I have done it earlier, and this is a mixture of a compound, and you can see the sample which is has been more affinity towards the stationary phase has eluted last, and less which has the less affinity has eluted at the first. And according to that, the retention time has obtained, and all the area of the graph and percentage area and height has been automatically integrated by the software. For a mixture of compound, what we have to be careful about is, if a mixture, for example A and B, is there, and both A and B have same affinity to the stationary phase, then we have to select the mobile phase in a way that either A or B will have more affinity towards that, and it will come first and the other late. And if say in the second case, if A and B have same affinity towards the mobile phase, then we have to choose stationary phase in such a way that either A or B will have more affinity towards it, so that it will come later, and the other with the less affinity comes towards the stationary phase will come last. In this case, we can see the three peaks in a separate retention times in a mixture, and the retention time is calculated from the injection point 0 to the peak maxima of this particular peak. That is how it is calculated. For fluorine, you can see the retention time is 9.056. Next it is 9.779, and anthracene it is 10.473, and the peak height is calculated from the baseline to the peak maximum. This is how particular peaks of a HPLC graph is. For a mixture, it is shown like this with separate compounds, and for a single compound it is shown as a single peak. Thank you.
Now we saw how to detect the presence of a component in a sample. Now we are going to see how to calculate the quantification part of the compound. Here I am showing the quantification of the naphthalene.
Now we are going to demonstrate how to interpret HPLC result for naphthalene using a standard calibration curve. This step is essential for quantifying sample concentrations accurately. Here we can see the areas from the chromatograms obtained for a series of naphthalene standard solutions. Here we can see a standard curve plotted by placing the peak area on the y-axis and the concentration of the naphthalene in mg per ml on the x-axis. Along with the standard curve, we can see a linear equation obtained from the standard curve y is equal to 0.0441x plus 0.0033. Now we can rewrite the equation here.
This standard curve we took from a research paper. Using the standard from that research paper, we calculated the naphthalene content present in our sample.
From that we can find out the concentration of the naphthalene. Here x, the area we got is equal to 3037 From that we can find out by substituting the x value in the equation, we can find out the value of y, that is the concentration, that is y is equal to 0.6138 mg per ml. Thank you.
Here, the x value we took from the area of the naphthalene peak that we saw in the previous, before the quantification of the naphthalene. From that, we took the x value and we calculated the concentration of the naphthalene using substituting the x value in the equation. Now we saw how to interpret uh, the HPLC result using the standard curve and using the reference that already present in the HPLC system. So sorry for the discomfort. Now we are going to discuss about UV spectrophotometer. UV spectrophotometer, we already have discussed the theory part in the morning. So UV spectrophotometer is an instrument that is widely used nowadays in industries for analysis and all. So I think most of you have or might have at least seen the instrument in your lab or some other lab. So we are going to discuss about UV spectrophotometer. UV spectrophotometer is an instrument that measures the light absorbance of a sample in the ultraviolet region. Here we are using UV spectrophotometer. That is why we are discussing about the ultraviolet region. If we are using UV visible spectrophotometer, we can we can use both ultraviolet and visible light region. It is applicable for both qualitative and quantitative analysis. It has some parts like light source, monochromator, sample holder, and a detector. Here, we are using for the demonstration. We are using double beam UV spectrophotometer. Here, it will split the light from the source into two. One part will go through, pass through the blank, and another part will go through, pass through the sample, so that we can find out the concentration of the compound that we want to detect by comparing with the absorbance of the blank. And here we have a sample holder. In that the sample holder, we will keep the cuvette. Cuvette is a transparent container in which we are transferring the sample for the analysis. For the cuvette, it will have four sides. Uh, Two opposite sides will be transparent, and through the transparent side, the light will pass, and the other two sides, opposite sides, will be translucent. That sides will not come in contact with the light, and a detector also will be there. Here, the light passes through the sample, and as the light passes through the sample, the component present in the sample will absorb the light that passes through this, and based on the absorbance, uh, some after the absorbance, some light will be transferred through the sample, and by taking the transmitted light, we will analyze the, or we will find out the absorbance of the sample, and by putting the same value as we did in HPLC, using standard curve, we can find out the concentration of the compound present in the sample. Here we are using Beer-Lambert law for the, that is the principle behind UV spectrophotometer. According to this, the absorbance of the sample is related to the concentration of the uh, compound present in the sample. It means as the compound, for example, if we need, we are analyzing the total phenol content. If the phenol compound are more in the sample, then the absorbance will be more. It will absorb the absorb more light, and if the concentration is very less, then the absorbance will be very less. So here also, I already told that when we are doing some analysis or some research work, we have to know a thorough idea about the analysis we have to do for the sample. So before that, we have to know like at least little bit idea about the instrument that we have to handle. So we know, we now we can understand what are the specifications and the significance of the UV spectrophotometer. Here we, like the question, we will think why we are using spectrophotometer. That is, it provides vital information about samples composition and concentration. Here, it is a fast, non-destructive, and sensitive method used for analyzing pharmaceuticals, proteins, nucleic acids, environmental samples, etc. It helps to identify compounds and determine the purity and concentration. Here, this is we can use for both qualitative and quantitative analysis. Now, we can discuss how to use the UV spectrophotometer. First of all, we have to prepare the sample. For that, we have to mix the sample with the required solvent. After that, if it is required, we have to filter the sample, because if the solid content is more, it will increase the absorbance of the light. So that before we are transferring the sample into the cuvette, we have to filter the sample if it is required. Next, we have to select the appropriate wavelength, because as we discussed in case of HPLC, each compound have its own specific retention time. Just like that, here each compound will absorb light at a specific wavelength, and it will then we have to pass UV light through the sample. Then it will detect the transmitted light. It will measure the transmitted light, and based on the amount of transmitted light, we can find out the absorbance of the sample. Then the instrument will convert the absorbance, and display the absorbance value of the compound. Now we can discuss the application of the instrument. It is used for quantitative analysis of the sample using absorbance. Here, I will show it in the demonstration of the instrument. Here we can know how much amount of compound, the specific compound, if we are analyzing the flavonoid contents in the sample, then we can analyze how much uh, amount of compound is present in the sample by using the absorbance using the standard curve. Next, we can do it for the identification of the organic molecule based on the spectra. I already discussed that like for each compound, there will be a specific absorbance and the wavelength of the light that it will absorb. So the wavelength, the light that absorbed by protein will be different from the wavelength of the light absorbed by carbohydrate. So based on the wavelength, we can identify the organic molecule that present in the sample. Next, we can test the purity of the sample present in it. For example, if we are analyzing the adulteration in oil, the absorbance of component present in the edible oil will be different from the adulterate that we are adding in the oil, the edible oil. So based on that, we can understand how much quantity of the adulterate or other impurities present in the sample. Next, we can use it for enzyme and protein concentration measurement, then monitoring the reaction kinetics. For example, I will give a simple example. In case of the thermal heating or processing of fruit juice is rich in antioxidant that we all know. When we are treating it with a high temperature or we are keeping the sample for long duration at a specific time, or we are heating the juice. For example, I will explain with the juice. If we are processing a fruit juice, we are keeping it in a temperature for long time, or we are heating the juice for a specific duration, or we are increasing the temperature of the heating process. We all know that the antioxidants are very sensitive to light temperature, so it will the quantity of the antioxidants will get reduced. So after each time, if we are keeping a duration of a gap of 15 minutes, after 15 minutes we can see how much amount of antioxidants present in the sample. So we can monitor the reaction kinetics and water and environmental pollutant analysis, as we told in HPLC. We can analyze what are the compounds present in the or the pollutant present in the water uh, by analyzing it using the UV spectrophotometer. Next, we can use it for the food and beverage quality analysis also. So here also we have to discuss the limitation. It is susceptible to errors from stray lights which affect the accuracy, especially at a low absorbance level. If the concentration of the sample is very less, it can be the results can be affected by the stray lights. And the samples with the particulates, bubbles, or turbidity scatter lights, causing inaccurate absorbance reading. If some particulates or bubbles are present in the sample, it can affect the absorbance value, so that it will give the inaccurate result. And the sensitivity issue with the very low concentration sample, it may require sample preparation and pre-treatment. If the concentration of the some specific compound in the sample is very low, will be very difficult to analyze using UV spectrophotometer. So we have to go for some other technique. So next is the instrument calibration affect the stability and reproducibility of the instrument, and it cannot be efficiently analyzed solid or gases without additional adaptation. These all are the limitation. In addition, we have to be careful while analyzing the using the UV spectrophotometer, because the cuvette should be clean, because if some dust or some particulates are present on the cuvette, it will affect the absorbance of the sample, so the result will change. So we have to be careful while using the uh, spectrophotometer. And when we are doing the demonstration, or we are using the UV spectrophotometer, we have to keep the uh, instrument on for minimum 20 minutes. It ranges with it depends on the instrument. It ranges from 10 to 30 minutes. It is because it is considered as a warming time, because it is for the warm up time we have to give this, because the light when we are switching it on will not give the accurate or the sufficient amount of light, so we have to keep it for warming up. So next we are seeing how to prepare the sample for analysis of the sample using UV spectrophotometer.
Everyone, we are here for the quantification of total polyphenol content of fruit juice using UV visible spectrophotometer. For TTC, the standard is used as gallic acid monohydrate. Chemicals required for TTC are 7.5% of Na2CO3 weight by volume, 1:10 volume to volume ratio of FC reagent, gallic acid as a standard, and distilled water. Firstly, for the standard preparation, the stock solution will be prepared by adding gallic acid in distilled water at a concentration of 100 mg per ml. Then the stock solution is being diluted to 20, 40, 60, 80 and 100 mg per ml by adding distilled water. Now distilled water will be added to cover the volume. Now, in each test tubes, 2 ml Na2CO3 solution is added and kept for incubation for 5 minutes. After 5 minutes, 0.5 ml of FC reagent solution is added to each test tube and is shaken well. All the test tubes are kept for incubation for 60 minutes at room temperature in dark. Then the absorbance of each solution is taken against blank at 760 nanometer using UV spectrophotometer. The blank is prepared by adding all the chemicals and reagents except sample. This is the blank. Fruit juice is diluted into 10 times using distilled water, and similar protocol is used as done in standard solution. Instead of stock solution, diluted fruit juice is used. This is our fruit juice sample and we will dilute it into 1:10 ratio. Now, all the other reagents will be added. After 5 minutes, FC reagent is being added. The absorbance of the solution is taken against blank at 760 nanometer using UV spectrophotometer. Later, we will discuss about quantification of phenolic content of juice in result interpretation.
Here we kept the samples, all the samples in light. Actually, we should not keep the samples in light because it will because the FCR is photosensitive. But we kept it open to show you people. So next we are going to see how to do the demonstration of the of the UV spectrophotometer.
This is the UV spectrophotometer. First of all, we have to turn the spectrophotometer on and allow it to warm up for 20 minutes. Then fill the blank in each cuvette and place the cuvette in cuvette holder. As the light passes through the transparent part, ensure that it is clean before use. First of all, we have to set the wavelength. For that, press the wavelength option, then set the required wavelength. For TPC, the required wavelength is 765 nanometer. Then press OK. Now we have to set the absorbance of the blank to 0. For that, press 0 option. Now transfer the sample to the cuvette and place the sample cuvette in the sample cuvette holder. After pressing start button, we will get the result on the screen.
Now we saw the demonstration of the UV spectrophotometer. Here I already told for each component we have specific wavelength that it will absorb the light. So here for TPC it is 765 nanometer. Now we are going to see how to interpret the result of the uh, UV spectrophotometer analysis.
From the experiment, we got to know the absorbance of the total phenolic content of the fruit juice using UV visual spectrophotometer. Before going for the quantification of TPC of the fruit juice, first we will determine the equation between the absorbance and concentration of phenolic content. The equation can be estimated from the absorbance of different concentration of stock solution of gallic acid. Concentration of gallic acid in microgram per ml. Here we will write the concentration which we have taken 0, 20, 40, 60, 80 and 100. Previously, we had taken the absorbance of known concentration of gallic acid, which will be writing down here. Absorbance
For many people, it is not able to see the video, so I am resharing the video again. Sorry for the inconvenience.
From the experiment, we got to know the absorbance of the total phenolic content of the fruit juice using UV visual spectrophotometer. Before going for the quantification of TPC of the fruit juice, first we will determine the equation between the absorbance and concentration of phenolic content. The equation can be estimated from the absorbance of different concentration of stock solution of gallic acid. Concentration of gallic acid in microgram per ml. Here we will write the concentration which we have taken 0, 20, 40, 60, 80, and 100. Previously, we had taken the absorbance of known concentration of gallic acid, which we'll be writing down here. Absorbance zero point 0.1559, 0.2675, 0.5239, 0.7783, 1.0448, 1.3069. So these are the absorbance of the gallic acid. So now we will be plotting a graph from these values. So here graph is plotted. The graph is linear graph, and the equation of the linear graph should be in the form of y is equal to mx plus c, where y is equal to absorbance, x is equal to concentration of gallic acid, m is equal to slope of the equation, and c is the intercept. From the current graph, we got to know that we will get the equation from the current graph by clicking display equation on the chart and display R squared value on the chart. So this is our equation and R square value. This is the linear expression between the absorbance and concentration of gallic acid. Now we have to take the concentration of the sample. Suppose if the sample's absorbance is 1.038, we can write over here absorbance of sample is 1.038. We are taking this as an example. While in the case of sample, we know only the absorbance value, from where we will estimate the concentration of phenolic content of the sample fruit juice. So here we will put y is equal to 1.038. and we have to find X. So putting this value in the equation, X is equal to X is equal to 1.038 minus 0.0837 whole bracket divided by 0.0119. So here X is the 80, X is the concentration of the total phenolic content present in the sample in the form of microgram per ml. So here 80 is the concentration. Hence the concentration of the juice is concentration of the juice sample is 80.193 microgram per ml. Thank you.
Here, some people couldn't watch the video properly, so I will brief the result interpretation of UV spectrophotometer. Here, we got the gallic acid concentration and its absorbance. We just charted it, and using the values, we plot the graph of the result as x in x-axis is concentration of gallic acid and y is the absorbance. And based on the result, we plotted the graph and we got the uh, linear equation from the graph as y is equal to 0.0119x plus 0.0837 with an R square value of 0.09891. So by substituting the x value in the equation as we did in case of HPLC, we will get the concentration of the sample. Here we can see the absorbance of the sample with the of the gallic acid with 80 and 100 microgram per ml has absorbance above 1. Actually, for this UV spectrophotometer, it should not be above 1. It is because the concentration of the sample is more. So we have to dilute the sample so that we will get the accurate value. Here, if it goes above 1, then it will reduce the accuracy. It should be in between 0.1 to 1. And in the chat box, there was a question came that how to analyze the solid and semi-solid samples. For solid and semi-solid samples, uh, we can mix it with the required solvent. In case of antioxidant activity of some leaves, we can say for dried leaves, we can mix the powder of the leaves, dried sample powder in with the solvent, and we can extract the antioxidants present in the sample, and we can use the after filtering or centrifugation, we can use the clarified uh, solution for the analysis. So now we saw how to do the result interpretation of UV spectrophotometer. Now we are going to the next instrument. Now we are going to explain about or discuss about Fourier transform infrared spectroscopy. Here, it's an instrument used to identify the functional groups and to determine the molecular composition of the sample. It analyzes how a sample absorbs infrared light and produce a unique molecular fingerprint. It is used. It uses an interferometer to measure all infrared frequencies simultaneously and by speeding up data collection compared to the traditional method. Here, the sample absorbs specific infrared wavelengths. Here, we can see in case of HPLC, we were doing we could see that it had a specific retention time. In case of UV spectrophotometer, we could see it had a specific wavelength to uh, absorb. In case of this FTIR, we can see it has a specific IR infrared wavelength corresponding to molecular vibration, and its absorption spectrum identifies functional groups and molecular structure. For each bonds and compounds present in the sample will have its own specific wavelength, and it will absorb the infrared at the wavelength, and it will start to vibrate uh, at a specific frequency. So as we discussed in case of HPLC and UV spectrophotometer, we have to know why we are using FTIR and how to use the FTIR. FTIR is a high sensitive simultaneous measurement of all frequencies and accurate molecular characterization without extensive sample preparation. It is a non-destructive, fast scanning and precise molecular identification without external calibration. It needs, I think, maximum 5 minutes for the analysis, and for the data interpretation, we have to use software. Here, it helps to identify the compounds and determine the purity and concentration of the sample. Now, we can discuss how to use the FTIR. The sample is, first we have to expose the sample to the infrared light, and at specific wavelength, it will absorb and like by the different chemical bonds. And there will be a interferometer. It will split and recommend the infrared beam to produce an interference pattern containing all wavelength data, and the instrument converts the interferogram. The interferogram will be get from the FTIR into IR spectrum and showing peaks that represent the molecular vibration and functional groups. So we can discuss the application of FTIR. Uh, FTR is used to identify the functional groups and organic molecule, because for each functional group it will vibrate in a specific manner. So we can identify which compound is present or the functional group present in the sample. Next, we can use it for the characterization of the material as we discussed before, and it can be used for the qualitative analysis of the chemical compound present using the infrared and absorbance, because for each compound it will vibrate in a different manner. So we can identify the compound present in the sample. As using the same method, we can identify, like we can determine the purity testing. We can do the purity testing for pharmaceuticals, chemicals, and raw materials. And here the monitoring reaction and monitoring reaction kinetics and real time process tracking also can be done using FTIR. And the quality assessment in food and beverage also we can do using the FTIR. So each and every instrument we can use for the same purpose, but it depends on the sample. That is the difference. So next, we can discuss the limitations of the FTIR. Its limited sensitivity for low concentration analysis due to weak infrared absorption. If the concentration of the compound is very less, then the sensitivity will be less, and the absorption of the infrared also will be less. So its vibration will be comparatively less. That will may give the inaccurate result, and there will be overlapping peaks that can make the spectra interpretation complex and reduce the specificity. If in case of some compounds having nearly same wavelength for absorption, it will vibrate, it will absorb almost nearly same wavelength infrared, and it will start to vibrate. So there will be a chance of overlapping of the peaks. So it will reduce the accuracy, and it will be difficult to interpret the spectra. So next, the limitation is it requires careful sample preparation due to avoid spectral distortion. Because in case of thickness is an important factor for the sample. Actually, we don't need a sample preparation. We just need to give the sample. It can be liquid or solid. but the thickness is an important factor because as the thickness increases, it will not absorb the uh, it will not absorb the infrared as it requires. So we need the thickness which should be less than 10 micrometer, and uniformity is also an important factor. If it is not uniform, then the absorbance will be affected. And in case of dryness, if moisture content is more, we have to there will be absorption of infrared rays by the moisture, the water present in the sample. So it will affect the result. So next is the poor penetration depth restrict the analysis to surface layer. In case of some sample, if the thickness we already have told, the thickness is more, then it will analyze the surface layer only. It will not go inside, and the inside part will not absorb the infrared. So it will affect the result. Next is the result can be affected by the environmental factors like temperature, humidity, and carbon dioxide interference. In case of temperature, when the temperature fluctuates, it will affect the absorbance of the sample by the infrared rays absorbance by the sample. In case of humidity, as we discussed in case of dryness, as the humidity increases, the moisture will absorb the infrared and it will affect the result. The accuracy will be reduced. In case of carbon dioxide, the ambient carbon dioxide has a property to absorb the infrared rays. So if carbon dioxide is present in the sample or the present in the atmosphere around this, then it will affect the result. So we will set before analyzing the sample we will set the restriction of these all interference before the analysis of the sample. So next we are going to see the sample preparation. Uh, this is the sample preparation of FTIR. There is no need of sample preparation for FTIR, but we can see the video. Let's see.
Good afternoon, everyone. Today's practical session is about the demonstration of FTIR spectroscopy. There is no need of preparation of food sample. The sample can be experimented as it is. Both solid and liquid food sample can be tested through their FTIR spectra. For FTIR spectra, we are taking freeze-dried bioactive compound extracted from leaf as sample.
Now we can see how to do the demonstration of the FTIR.
Here we are going to explain the attenuated total reflectance FTIR. The ATR FTIR is a simple non-destructive method that requires minimal or no sample preparation and is used for fast analysis compared to traditional FTIR.
In case of traditional FTIR, we have to treat it with the potassium bromide or some other compounds. Then only we can use it for normal FTIR. And in case of ATR FTIR, we don't need to treat it with any compounds or we don't need any sample preparation.
This is the FTIR software interface used to run the analysis. Before starting the measurement, we first open the software and make sure that the instrument is connected. First, we need to do the settings. In the settings menu, we need to set the result spectrum. Here, we have different spectrum modes: absorbance, transmittance, Kubelka among reflectance, long reflectance, AT spectrum, and PA spectrum. Generally,
In case of reflectance, reflectance spectrum, the analysis done by taking the reflected how much infrared is reflected by the sample. In case of transmittance spectrum, we are analyzing based on the amount of infrared transmitted by the sample, and like that, in case of absorbance spectrum, it will be analyzed based on the amount of infrared absorbed by the sample. And in case of long reflectance, it is used for the surface treatment or surface analysis of the sample. And in case of a PA system, it is used for analyzing the sound that produced during the uh, interaction of the infrared with the sample.
we choose transmittance or absorbance mode. Here, we can set the data save range. It starts from 400 to 4000 centimeter inverse. With this, we can change the background scan time and sample scan time. It should be the multiple of 16 to avoid the noise and to get accurate and stable spectra efficiently. To remove atmospheric interference and obtain accuracy, we have to do background scan. It is done by clicking background single channel, then accept and exit.
Here we have to wait till we restrict the interference and wait setting the instrument for the analysis. So here we have to wait for that.
Here we keep the sample and shut the knob.
After keeping the sample, we have to go to the settings menu again, then sample signal channel and start the measurement. This is the graph. We can do baseline correction here by clicking on the baseline correction option. Then select the sample and click on the correct option. Here we can save the result in different modes like OPUS format, data point table, pirouette DAT, JCam TX, Galactic, ENVI, Allotrope, XML, MATLAB 4, MATLAB 5, and IMZ ML 1.1. Generally, it is saved in data point table mode. Select it, give the sample name, and save it.
Now we are going to see the result interpretation of the sample, that the result we got from the FTIR. Here we are using Origin Pro software. We can use many other softwares like Spectragraph and essential FTIR, but here we are using Origin Pro software for the data interpretation.
So after the data curation from FTIR, we get the data like this. We can just copy the whole data from here, and after that we have to go to origin. So in a origin book sheet, we have to just put the whole data in x-axis and y-axis. After that, we have to select the whole data, and we can just plot from here in the line graph, or we can just right click and we could go to the plot and the line symbol. So I'm doing from here. So the plot will be looking like this. After that, to make it look good or for our convenience, we can rescale and we can replace the ticks and lines. So I'm putting from 4000 to 500 because we have taken for the analysis from 500 to 4000 centimeter inverse. Just apply it. And for vertical, we don't need the tick labels, and we will just keep all the lines and ticks. So we can go here, lines and tick option. For the bottom, we don't want the minor ticks. For top, we can keep the line on only. For major and minor ticks, for both, we will select none. For left, we want line, but because we don't have labels, so we don't want any ticks. For the right side, we want line, and again, we don't want any ticks. So we can do none for all, and we will just after that we can click OK. After that, here we can write, since this is upward peaks, so this is absorbance, and its unit we can keep arbitrary unit, or sometimes people are keeping a percentage also. So here we are keeping arbitrary unit, and this x-axis is our wave number, which unit is centimeter inverse. So that's how our plot will look like. The original plot will look like. After that, here we can see a lot of noise here, and in this area or in this area we can see a lot of noise here. That may be some error in the instrument or some mishandling of the sample also. So we don't want this error in our curve. So to remove this noise, we can go to the analysis. We can smooth our curve. So for here, we can go to signal processing. After that, there is a smooth option. In that, we can go to the open dialog. In here, we can see that there is one polynomial order. In that one, we can select 5, and the number of points of windows should be greater than 5. So it depends on how smooth the graph we want. So in our graph, there is not that much noise, so I'm keeping it as 30. And here we can select auto preview to see the how the our smooth curve will look like after this, after applying this option. So as I'm applying this option, we can see there now there are two curves actually. So one is bioactive compounds, which is our black one, which is our original graph, and one is that 30 points smooth curve of bioactive compounds, which is in red color. So here, after going to object manager, we can deselect the bioactive compounds or original graph, and here we are only seeing this smooth curve. After this, we are interested to find the peaks, because the peaks are the ultimate goal from which we can find these what to say that our functional groups, because all of functional groups or bonds, chemical bonds, are assigned to these peaks, but we cannot find it exactly find it by manually by clicking here. So there are option. So first we will just make it more thick to make it more visible, and after that we can go to this analysis to find the peaks. We can go to the peaks and baseline option in analysis, and there is one peak analyzer, and then we can go to the open dialog. And open dialog, there is two dialog box will be opening. One is this pop-up window, and another one is background of this graph, which is actual graph or a smooth curve, which magnified more to make it more visible. So we need integrated peaks, and we want to recalculate as manual. So we can directly go to the next part, and we want the minimum because this is absorbance. So we want to keep the baseline as minimum. If it was transmittance, the peaks would have been inverted downside. So at that on that case, we would select maximum. So for here, we need this minimum y, and we will keep baseline mode as constant also. After that, we can directly go to this next, and we don't want to subtract the baseline because the baseline correction was already has been done from the FTR instrument. We can directly go to the next, and here we will find this one button as find. You can see there, and this enable auto find is already been selected by the software. So as I will click this find button, it will find all the peaks. So here we can see all the peaks are there, and so we can just note it down. We can just note it down, all the peaks. For example, 32379042829227. This all the peaks are here. If we don't want any peak or we want more peaks, so we can do that also. We can just uncheck the enable auto find. We can go to the peak info. I can deselect this one. I can deselect any of the peaks, and that will be disappeared from this curve. Or if I want to modify or delete, I can go to this button. I can add more peaks also. I can delete any peak or any peak too. So after this, I can directly finish, and that will be there will be one what to say book also, or it will be written here also. And in the book, now if I will see in the book also, all the peaks will be written here. 1, 2, 3, 4. These are here, and the area under the peak also are here, and the beginning and ending of the peak from where the in the curve it is starting and where it's ending, and the center of this peak. Actually, this is our peaks, and we can find peaks like this. After that, if I want to make a graph for presentation of a paper, research paper, or anything, PPT or presentation. So I will just note it down for myself. I will just delete everything because I have already noted down the peaks. Now if you see, our graph is clear. So for now, as I have already noted down my peaks, I can go to the line, or I can go to any of this tools, arrow tools. I can do like this. I can go to the text, and I will write it 3233.79 because this is the peak which I have found for this one. Same thing I can do for this. I will write it here 2927.67. Similarly, I will do for everything. If I want to reduce the size of this also, I can reduce because it will get more clumsy if I'll keep higher font size. Or if I want to represent my this broad peak as a spectrum, I can go to this rectangular box because sometimes people are using it as a spectrum. So here I can increase the transparency. I can change the color also. So that's how people are also showing the band of the peaks, because it's very broad peaks. So we cannot say that exactly this is the peak which is only matters. So people are showing bands also for this. And for now, to show you that what the peaks are assigned for, and I will, for the convenience, I will just mark all the peaks 15, 71.69, and 3, 97.06. Let's keep it 4 only to save the time. And I will tell you how to find this assigned peaks, for what these peaks are assigned for what kind of chemical bonds, or what kind of functional group they are assigned for. So you can find the peaks what they are assigned for in the any reference library in from the internet or from any research paper. So I have one good research paper here. So I will just import it here. For example, this graph is here. This I have taken from from a review paper or research paper. So this is, you can find it in the Google Scholar. So as we have got this peak 3233, so we will just check on the what range of wave number range it's coming, it's falling, and what are the functional groups or stretching, bond stretching it's assigned for. For example, 3233.79, this is falling in this region, 3000 to 3600 region. So this is actually showing that OH or NH bond is stretching, which shows the functional groups like water. It may be because of the water, alcohol, phenols, carbohydrates, peroxides, polysaccharides, lipids, or carbohydrates. Any of this can be there because of the reason this peak is coming. So for next peak like 2927 is falling under this reason, like 2800 to 300, 3000. We'll zoom it out from this region, which is showing CH2 and CH3 stretching vibration, and which is basically assigned for the lipid acyl chain, which is showing lipid acyl chain. Similarly, for other peaks like 1571, this is for this reason, wave number range of 1500 to 1600, which is showing aromatic and NH bending vibration, which is showing amino acid. Similarly, for other peaks also like 1397, which is coming in range this one 1300 to 1450, which is showing primary or secondary OH bending in plane and phenol or tertiary alcohol OH bending. We can find these structures from the internet easily, which is present in phenyl groups, which is confirming that there is a phenyl group present in the our raw material. So this is for the bioactive compound. So obviously there are some alcohols, phenols are there, and phenyl groups are there. Some aromatic chains are also there. So so that's all about all this FTIR analysis. So thank you.
So that's all about the result interpretation of the FTIR. So it's the time to time for the question and answer session. That concludes my presentation. I would be happy to take any question you may have. If you have any questions, you can ask me. You can message in the chat box also.
Rashmi, if there is no question, we can conclude the session. Thank you very much for explaining the concepts, very neatly. Yes, I think somebody want to ask. Sashwat Tiwari.
I have explained the answer for the question. For all this, in case of HPLC, we can analyze the uh, for HPLC, we can analyze the both liquid and solid sample. In case of that, we have to mix the sample with the solvent, and that we have to mixture we have to take or the measure for the analysis. In case of UV spectrophotometer also, the procedure is same, but the solvent will be or the procedure will be different. Like the chemicals we are using and the reagents we are using will be different. And in case of FTIR, we can use both the liquid, solid, and semi-solid samples for FTIR. And for the weighing, we know there will be specific procedure for each analysis of each compound. So for that, there will be specific for in case of uh, TPC or DPPH of leaf, for example, leaf materials. We can take it in 1:10 ratio. It depends on the sample we are taking, and we can extract the sample and we can
Rashmi,
take the extract from the sample.
Rashmi, what is the question? Like, you please tell the question as well so that everyone can understand. What is the question?
So it is they are asking how will we weigh the liquid sample and semi-solid sample. We don't need to weigh the we don't need to weigh the liquid sample. It is in case of semi-solid and solid sample, we have to mix it with the solvent according to the procedure, and we have to measure it in ml.
Okay.
That is what I
You're asking
explained.
for.
There is one more question in the chat box. Can't we plot the FTR graphs by using Excel sheet? Yes, it is possible if you have raw data with you. You can plot it in X and Y axis. You can get the result as shown in the computer connected with the FTIR. Okay, it will look like in the app.
Yeah, for the question, like most of the FTIR equipments are coming with FTIR software where it gives you a direct graph. So no need to plot it against Excel sheet. Maybe in case if you have a raw data from received from any article or some other database, then you may have to go for Excel sheet, or else directly this FTNIR softwares will give you the slides. We'll see you the
Especially
graph.
for publication purpose, to increase the clarity in the papers, you can go with Origin Pro, Origin, or any kind of softwares. You can feed the raw data, and you can get the graphs, clear graphs. Then you can use it for the publication.
Any other doubts coming in the chat box? I'm not able to see the chat box. Messages in the chat box.
I think it's almost 4 o'clock, sir. We can conclude the session.
Okay, fine. Go ahead.
Yeah. Any other questions we will take up in the WhatsApp group. Okay. Thank you very much, Rashmi, for clearly explaining the concepts of the HPLC, GCMS, FTIR. You have clearly explained. We will take up the question and answer session in the WhatsApp group also. Okay. Thank you. I think we can conclude the session. Tomorrow morning at 10 o'clock, we can meet again for the day 3 sessions. Okay. Thank you very much. Very good, Rashmi.
I stuck somewhere, sir.
It's okay,
Some
no problem.
technical error.